Motor Imagery BCIs, tackling noise and EEG data. Imagine controlling a computer or a prosthetic limb just by thinking about moving it. That's what motor imagery brain-computer interfaces aim to do. But there's a big hurdle they face: noise in the EEG signals. EEG stands for electroencephalography, which records brain activity through sensors on the scalp. The signals are very faint and easily disturbed by other electrical activity or movements. This noise makes it hard to tell when someone is imagining moving their hand or foot. Electrical interference from nearby devices can add unwanted signals. Muscle movements, like blinking or jaw clenching, produce electrical activity that can drown out the brain signals. Eye movements also create artifacts that interfere with the data. Environmental factors like lighting and electrical noise from power lines can further muddy the signals. All these sources of noise lower the signal-to-noise ratio, which is a measure of how clear the brain signals are compared to background noise. When the ratio is low, it becomes difficult for the system to accurately interpret what the user is imagining. To fix this, researchers use several strategies. First, they apply signal pre-processing. This involves filtering the EEG data to focus on the frequency bands where motor imagery signals are strongest. Usually, this is between 4 and 40 Hz. Notch filters are used to remove power line interference, which occurs at 50 or 60 Hz depending on the country. Techniques like short-time Fourier transform or wavelet transforms help analyze the signals in both time and frequency domains. This makes it easier to pick out the relevant patterns. Next, spatial filtering methods like Common Spatial Patterns are used. These techniques transform the multi-channel EEG data to highlight differences between imagined movements. They help emphasize the brain activity related to motor imagery and suppress unrelated noise. Variants like Common Spatiospectral Patterns combine spectral filtering with spatial filtering to improve results further. These methods help extract features that are more resistant to noise. Feature extraction is another key step. Combining information from time, frequency, and spatial domains creates a more robust set of features. Some advanced techniques analyze the complexity of EEG signals using entropy measures or look at how different brain regions connect during motor imagery. These features help machine learning algorithms distinguish between different imagined movements more accurately. Machine learning models, especially deep learning ones like convolutional neural networks, are now used to automatically learn the most relevant features. They can adapt to individual differences and handle noisy data better than traditional methods. These models are trained on large datasets to improve their ability to classify motor imagery signals correctly. Since EEG patterns vary a lot from person to person, adaptive algorithms are important. They customize the frequency bands and channels for each user, reducing the impact of noise and improving overall performance. This personalization makes the system more reliable for practical use. In real-world applications, these noise reduction techniques are vital. For example, in rehabilitation, motor imagery BCIs help patients control prosthetic limbs or assistive devices. Better noise handling means more accurate control, which can make a big difference in daily life. Overall, combining filtering, spatial techniques, advanced feature extraction, and machine learning helps turn noisy EEG signals into clear commands. This progress pushes forward the development of more effective and user-friendly neurotechnology devices.